As of for today, we are going to talk about digital signal processing, classification of discrete time signals, as well as its periodicity and symmetric sequence, or even and odd properties. So, but during this discussion, we are going to divide this into two parts. The first part will be classification of discrete time signals and periodicity, and the other part is symmetric sequence, even and odd uh, signals. Okay, so let's get started. So this is my very first video about digital signal processing, and I hope you will like this video and you will learn a lot from this discussion. Okay, so there are so many ways to represent discrete time signals. Okay, so basically we're going to tackle four very briefly. So number one, we have graphical representation. Number two, we have functional representation. We have tabular representation, and number four, we have sequence representation. So let's go first with the graphical representation. So when we talk about discrete time signal, meaning right, the amount of the amplitude of the signal as well as the x of n, or the n, the position of the signal, okay, is discrete. Okay. So for example, we have a graphical representation of this signal. We know that the value is x of n. We can represent discrete time signal in the value of x of n and equal to the value of the amplitude, whether that amplitude might be zero, negative, or a positive value. So in this case, we are going to represent the signal in terms of x of -2 is -3. So this talks of your x of n, its position, okay, in the x-axis, and then the value of the amplitude. So for example, if we take x of -2, taking into reference, okay, n equals 0, so that is our n equals 0. You also have n equal -1. You also have n equal -2. So if we're going to represent the signal x of -2 with a value of -3, so it means the position is in -2 of the n, and its amplitude is -3, so that we will be having this kind of signal here. So we have this kind of signal here for the position x of -2. And the same as with the x of -1, we have a value of the amplitude of +2, so that we can represent that discrete time signal in this one. X of 0 equals 0, so we have a value of 0 in the n equals 0. So we have x of 1, amplitude of 3, so we have the position for n equals 1, okay? Its amplitude is +3. So we have here as x of n, amplitude of 3, and we have x of 2, so position is 2, and of course the value of n is 2. Then we have a value of the amplitude as 1. And last but not least, we have x of 3. So we have the value of 2 as an amplitude. So this is the discrete time signal represented by graphical representation. Okay, so that's one way of representing discrete time signals. Number two, we have functional representation. So with this, the amplitude of the signal is displayed here for every value of x of n for the corresponding position n in the axis. So the amplitude of the signal is written against the value of n. So it means that its function is x of n. So with a values of the amplitude here. So here are the amplitude. So meaning if we have x of -2 for -2 x of n, so we have a value of -3. So for a value of x of -1, so we have a value of 2 as amplitude, and so on and so forth. So this discrete time can be represented functionally. So you may also get a function that is piecewise function, okay, if we are representing functional representation. Tabular representation is another straightforward, okay, representation of the signals that we have, of course. So correction, this is only -2. Yeah, so we have -2 and -1 here. So because the position of n indicates the position of the signal in the axis. So tabular representation, okay, these are the amplitude, these are the position. So same representation. Also, the sequence representation is one of the most used representation of discrete time signals. So finite duration sequence is given as follows. So we have x of n followed by a bracket. So we have, these are the values of the amplitude. Okay, these are amplitudes, right? And we have, if we can notice, we have an arrow there that denotes that n equals 0. So this will be your n equals 1, n equals 2, and n equals 3. So on the left side, of course, this would be your n equals -1, and this would be your n equals -2. So that's how you represent discrete time signal in a sequence representation. So if we see an arrow here, it represents that the signal on that specific value of amplitude is set at n equals 0. So the arrow indicating where the n equals 0. So we also have one property of signals. So we have periodic and aperiodic. So when we say periodic, the certain signal repeats at a certain period n. Okay. So we say that a signal is periodic if the signal x of n is periodic with the period n where n is greater than 0. N is the period if and only if the value of x of n, or the signal, equals equals x of quantity n, which n is any number plus the period. So if these two equates, okay, we can conclude that the signal is periodic. But if the given signal is in terms of let's say cosine or sinusoidal wave, so if x of n equals a, where a is the amplitude, cosine of 2 pi fn, of course, this 2 pi fn denotes the angular frequency, right? So 2 pi fn, then it is periodic if 2 pi fn equals a cosine 2 pi f, okay, quantity n plus n. So we can notice here that the value of n here, the smaller n, lowercase n, is added by another big letter n, which is the period, which is actually the same thing we applied here because that's the condition. Okay, so it is periodic as long as the 2 pi fn, okay, together with the period equals the 2 pi k. Okay, so anyway, later on we will understand how to solve those equations. So resulting in an f, okay, equals kn. So if we are going to equate this 2 pi fn equals 2 pi k, where k is any real number and n, uppercase n, is any the period itself. So we can notice that the 2 pi's will cancel, and we have frequency. If we isolate frequency, it can result to k all over n, where k is any number and your n is your period. Okay, so we can say, okay, that the signal is periodic if the value of n is an exact ratio. Okay, n should be a rational value. Okay, exact. So if n is 2, okay, upon figuring out the f all over k all over n, if n is 2, if n is exact 4, if n is equal to 6, n equals 12, these are exact number. So it is said that this is periodic. While if the value of n becomes 2 pi, okay, value of n becomes 3 pi, so that's irrational, we conclude it as aperiodic. It does not repeat itself over the process of a certain period. Okay, if there is no period that satisfies the condition above, it is said to be aperiodic. So let us try to solve some examples, okay, to test the periodicity and aperiodicity or periodicity of the signal. So check if the following signals is aperiodic or not. So let us start first with the first number. That is x of n equals 3 cosine of 0.5 by n. Okay? So the very first thing is that the solution to test if this is periodic, our concern is in the 2 pi fn. Okay? So this 2 pi fn, we are going to simply equate 2 pi fn with the value that we have here. What is the 2 pi fn to get the frequency? So we have 0.5 pi n. So, and this 2 pi, okay, 2 pi fn and 0.5 pi n, this n will cancel. The pi will cancel, so you are left with 2f equals 0.5 here. So the frequency would be 0.5 all over 2. And remember our formula a while ago is k all over n, where k is any integer. Okay, and if the n is rational or exact, okay, that's the period, then it means that it is periodic. So in this case, if we simplify this using our calculator, of course, that's 0.25. But the fractional part of 0.25 is what? Okay, the fractional part that is 1/4. Okay, so this is your k, and this is your fundamental period. So it means that this signal has a period of 4, which is an irrational number, exact number. So therefore, we conclude that this is periodic. Okay? So that's periodic. That's for number 1. So for number 2, we try to solve again the problem. So we have x of n. We have 5 sine of 0.1n. So what are we going to do? Again, get 2 pi fn, and that would be 0.1n. So as you can see, the n will cancel. So you are left with 2 pi f here equals 0.1. Get the frequency by dividing both sides by 2 pi. So you have 0.1 all over 2 pi. So this will be your k, and this will be your n. So your n in this case is 2 pi, which is irrational, not exact. If you evaluate 2 pi, that's around 6 point something, right? So therefore, our signal x of n is aperiodic. Okay, that's the number 2. Okay, so how about for number 3? So you have x of n equals sine or cosine of 0.125 pi n. Okay, so again, 2 pi fn, we want to get the frequency or the ratio of the k all over the period. So you have 0.125 pi n. Okay, so as we can see, the pi n will cancel. Okay, so pi and n, so we have 2f, twice the frequency all over 0.25. So divide both sides by 2, so we have 0.125 all over 2, which is what? If you're going to evaluate that, that will be 1 all over 16 in fractional form. Okay, so this is your k, and this is your period, fundamental period. So we have n, okay, equals 16. Okay, so it means the value of n or the period is rational, exact. So therefore, this signal is periodic. Okay, so that will be periodic. Okay, so that is for our number 3. So how about if for number 4, we have a signal that has complex, okay, sum of let's say a real number, okay, with e j pi n all over 12 plus the imaginary or the sum of this real number and this imaginary e raised to j pi of n all over 18. So we can recall that from our sinusoids or Euler's identity that we can resolve this into sum of cosine and sine. So we can rewrite this as x of n as the cosine of pi n all over 12 plus we have the sine of pi n all over 18. Okay? So now we have two sinusoids. Okay? If we have these two sinusoids added, okay, if we want to determine the fundamental period, okay, so we're going to determine only the fundamental period, but we will also see later that these two sinusoids have a period or periodic function because of the rational value of the value of n. So to find the fundamental period of these two added signals, so we're going to use the formula n equals n sub 1, where n sub 1 is the period of the first signal, multiplied by n sub 2 all over, which is the period of the second signal, all over GCD of n sub 1 and n sub 2, greatest common divisor. So the first, I'm going to get for the period of cosine part. So we have 2 pi Fn equals pi n all over 12. So cancel n and then pi. So we have 2f equals 1 all over 12. Getting the frequency or the fundamental frequency or the fundamental period, we have 1 all over 24. Okay, because of dividing it by 2. So this is my k, and this is my n sub 1. Okay, so my n sub 1 is 24, which proves that this is a periodic signal. So another one for the sine, we have 2 pi Fn. Okay, we have pi n all over 18. So cancel is pi n. So you have 2f or equals 1 all over 18. But if we're going to divide it both sides by 2 or cross multiply, so you have 18 times 32 is 36 divided by 36, you will be having f 1 all over 36, where this is your k and this is your n. So this would be n sub 2. So your n sub 2 would be 36. Both are exact rational. So to get the fundamental frequency, so our problem here, what is the not frequency, I'm sorry, the fundamental period. What is the fundamental period of the sum of these two sinusoidal? So by the way, okay, this formula, okay, also applies to multiplication of two sinusoidal. Not only plus, but in our example, it's plus, and as well as multiplication, we can apply this formula. So what is the fundamental period? The fundamental period would be n1 times n2 all over the GCD of n1 and n2. Okay? So we have n equals n1 will be 24, and we have 36 all over, what is the GCD? What is the greatest common divisor of 24 and 36? So it would be 12. Okay? So that's the greatest common divisor of between the n2 and n1. So 12 because it's the nearest divisor that we can divide 2. Okay? The two periods. 24 divided by 12 is 2. 36 divided by 12 is 3. That's the greatest common divisor. Okay? It's not 3 because they can be divisible also by 6. They can be also divisible by what? By 6. 9, it's not divisible because 24 is not divisible. So that's not the greatest common divisor. But 12, okay? So 12, 24, 12, 24, 36. So it becomes a 12. So upon calculating, the basic, okay, or the fundamental period of that would be 72. Okay? So that is how we are going to compute the fundamental period of that signal. So how about in number 5? Okay. So that's the example a while ago. So for number 5, last example for this, by the way. You have x of n e raised to j pi n all over 16. That would be multiplied by cosine of n pi all over 17. Okay? So this is multiplication. So we have here a e raised to j pi n all over 16. We have cosine here. So actually, we can get the value of 2 pi fn first of this signal. So you have pi n all over 16. So pi and n will cancel. So you have 2f all over 1 all over 16. So our frequency will over 1 all over 32, which is, this is your k, and this is your n1. So your n1 will be 32. On the other hand, computing for the cosine, the period, so n pi will cancel both sides. So you have 2f equals 1 all over 17, which is 1 all over 34. This is your k, this is your n sub 2. So that would be n sub 2 is 34. Okay? So if we're going to do that, get the value or the fundamental period. So you have n1, n2 all over the GCD of n1 and n2. So that would be 32 times 34. So what is the GCD of 32 and 34? Of course, the greatest common divisor of these two is 2. It's not 4 because 34 is not divisible by 4. Okay, it's not 6. Because 32 is not divisible by 6. 6, 12, 18, 24, 30, right? So the greatest common divisor is 2 only. So if we do that using our calculator, we'll be getting a fundamental period of 544. So that is the fundamental period. Of course, it still shows that it's periodic. Okay. So I hope you learned something from this lesson. I'm Engineer UJ Abad. If you're new to my channel, please don't forget to subscribe, like, and share, and join this channel. So for more digital signal processing videos, again, please tune in and subscribe to my channel. Thank you so much, and see you again when I see you. Bye.